Some good onions too. Very well aged.
Alright guys, I'm Ivan Bertasca. I'm a PhD candidate here. Been in the program for 9 years now. Got my bachelor's here, I got my master's here. I'm working my PhD. Hopefully I'll be out of here sometime this year. I've been working predominantly on control systems, and I heard that there was a lot of interest in MRC about control systems. So my first question is, what is your experience with control systems?
Dynamic systems.
Dynamic systems. Okay, good. That's a start.
EMD.
EMD, electromechanical design. Never took that course.
It's fun.
It's fun? Okay. I hear good things.
Depending on who you take it with.
Ah, okay. So are you guys familiar with second order systems, first order systems, Laplace transforms, ordinary differential equations, all that stuff? I hear a couple of smirks in the back. I hear somebody chuckling. So maybe I should take some time and go over some of those concepts just to refresh ourselves with it, right? So the most mathematically pertinent thing for controls is ordinary differential equations, right? So how many of us have taken eMath 1? So pretty much everybody. So we're all experts on ODEs, right? Yeah? Okay. So how about Laplace transforms, right? What is Laplace transform? Who can answer that?
Frequency to time.
Switching domains.
Domain.
Yeah. So it has to do with the frequency domain. It's not the full frequency domain because the transfer for the frequency domain is the Fourier transform, right? So the transform for the Laplace is actually into something called the S domain. The S domain is a combination of our frequency domain with a transient response domain, right? So whereas the frequency domain is just omega, the Laplace domain we have S, which is the combination of our sigma, which is our transient response, plus j omega, which is our frequency response, right? So we can actually get our Fourier transform from our S domain simply by setting that sigma term equal to 0. I'll show you guys that in a second, right? So I'm going to start off with an example. How many of you guys have seen a pendulum before?
Yeah.
Yes, everybody, right?
Yeah.
Okay. So if I say equilibrium point to you, what does that mean?
0 degrees.
One more time?
0 degrees.
0 degrees. Okay, so 0 degrees.
Straight down.
Straight down, right? So are you guys going to agree with me when I say that the pendulum only has one equilibrium point?
Yes.
The consensus, yes. Do I hear a no? Raul, do I hear a no?
Yeah, I'd say no at the top.
Exactly, right. So if we picture the perfect pendulum, right? So this is a pendulum that has no friction at its joint. It is free of any external disturbances. If we leave it exactly upright and there's nothing nudging it, it's going to stay upright, right? So really we have two equilibrium points on the pendulum. So we have a natural equilibrium point that we call stable, which is when the pendulum flops down and hits at that 0 degree mark. But we also have another equilibrium point. That equilibrium point is when the pendulum is 180 degrees apart from that, when it's straight up, right? Why is that important? Why do we care about pendulums so much? We like pendulums, right? Okay. So yeah, so we like pendulums, but pendulums are everywhere, right? So we're pendulums, right? Think about it. Where's our center of mass? Right here, right? Depending on how many sandwiches we had, it might be a little bit lower, right? So yeah, so the thing is that we're all inverted pendulums, and we talk about like really complex systems like walking robots. The most basic thing that you have to control is an inverted pendulum. So we have to design a control system to make that inverted pendulum stay up, right? So what are you guys' definition for control systems? Because I hear different definitions from everybody I talk to. I'm curious. If somebody asked you what is a control system, what would you tell them? That's great. That's a great definition for it, right? So we're constantly monitoring a system, right? So we have to have some kind of feedback to our system to make sure it's there. So I'm going to show you two examples. These are both of inverted pendulums. And there's really no difference to the physical plant or the physical system itself, right? The only thing that we're changing between these two systems are these coefficients that we're multiplying our sigma, right? So I'm going to start off with the first example. Hold on a second. MATLAB is deciding to use my screen as the first screen. So maybe if I do this, it'll be better. No, no such luck.
If you move it all the way to the right, it'll click on it and you can still probably see the
I gotcha. This is when it pays to know MATLAB. So we can see the actual time response of our system here. And I actually have a little animation I'm going to try showing you guys. Right. So let me try doing this one more time. So it makes it a little bit easier for you guys to see. Okay, here we go. So this is just my goodness. This is just a system that has a poorly tuned controller, right? So we're not able to actually get our pendulum up to that upright position that we want it to be at. What's happening is that we have a control system that sees that there's an initial offset in the pendulum of, let's say, 1 radian. So it's trying to compensate for it. So it gets up to that desired 180 degree position, but it overcompensates. So now we've gone a little bit further. So when we double back, we've actually gone further than 1 radian. Yes?
Is that like over damping, under damping, that kind of thing?
No. So when you talk about damping, that's inherently a stable system. So that means that if you do damp something, that means that you have a nice steady oscillation behind it. That's under damped, right? So it's not over damping and it's not under damping. This is actually something entirely different.
Okay.
This is stability, right? So this is important, right? So there's a chance that our controllers can drive our systems to instability. That's not good, right? So the most important concept in controls is stability. Right? So if we're using the pendulum example for the inverted pendulum, what that means is that we want to make sure that we're stable enough that we're able to get the pendulum from that initial position up to that upright position without it going crazy like we're seeing here. And if you take a look at the time response for it, this is something that you'll see in a lot of unstable systems, right? So we have our desired position by the dashed line. And the blue line is our time response of the system. So you can see that it's starting at an initial offset, and then it's overcompensating, continue to overcompensate on the other side, and continues to overcompensate. So that oscillation drives our system crazy, right? So I'm going to show you a second example.
The compensation going to continue to grow?
It's going to exponentially grow forever, right? Until we break our system, right? There's only so much that bearing that's holding that pendulum up is going to take. And then eventually after that, you're going to break that, right? So that's bad. Let me see if I can get this.
I don't know if you really want to have both screens, but you could just duplicate.
Double it?
Yeah.
Yeah. So now we have a nice stable system that hits that steady point really quickly, right? So what are the characteristics that we like about this system?
180 degrees.
Right.
No steady state error.
There's no steady state error. So Travis said steady state error. Who knows what that is? What is it? Yeah.
So when you're, in terms of, when you get to the point of the red line, I mean, you don't have a difference.
Right. So you don't have a difference there.
Are you within like 0.0?
Right. So if we look at it, we do have a small difference, but that eventually dies down. Right. So there's no steady state error. So steady state error would be a difference from our desired response and our actual response of the system. Right. So that's kind of a motivating example.
Are you on MATLAB to find your KPI and KPI?
Oh, MATLAB will do all that for you.
I mean, but that's what, you run the loop and then you're trying to find KPI.
So I'm not actively finding it. So I'm not finding it online, although that is something that you could potentially do with MATLAB. What I did is that I actually used another tool called PID tool, and it is an awesome graphical user interface. So no, it only takes in a linear system, right? So it's up to you to linearize that system for PID tool. Simulink, which is a program that's associated with MATLAB, that's actually a block diagram program, you can actually ask it to linearize things for you. And it'll linearize things for you, but by default, it'll linearize everything at t is equal to 0. So it's a dynamic simulation program which has some kind of time response to it. So when you linearize anything in Simulink, it does that at t is equal to 0. And it does that by default. So you have to explicitly tell it if you want to linearize it about another point. So always be careful with Simulink, and always read the instructions when you're working with Simulink. Hopefully we'll be able to get to that. I've already spent.
Change a different set. You can specify a different set point though for Simulink.
Of course. All right, so quick outline. I'm going to do some introduction to GNC. Who knows what GNC is? It's not a nutrition supplement company. I'll give you guys a hint. Anybody? Travis?
Guidance, navigation, and control.
President is doing his job. Good job. So yeah, so guidance, navigation, controls. Then I'll go through some mathematical fundamentals and background. I'll do some quick examples on Laplace transforms. Hopefully we'll have enough time for that. I'm going to go through the dynamic modeling of a mass spring damper system. I'm going to do that extremely quickly since you guys seem to be very familiar with vibrations or have taken vibrations or dynamic systems in the past. Then I'll go through some control system analysis and design. So we need to know how to analyze a system before we're actually able to design a system, right? So we need to know what we're working with before we're actually able to match our performance requirements. And then, time permitting, I will go through and do an example in MATLAB or Simulink, whatever you guys prefer, of tuning a PID controller or tuning whatever type of controller you guys would like. Or if you guys have another question about modeling some kind of system that you're trying to model, I'll be happy to work with you guys with that too. So, start off with GNC. So, guidance, navigation, controls, as Travis said. So in engineering, what we do is we take a large, difficult task and we break it up into smaller, simpler tasks, right? That's exactly what GNC does. So what GNC is pretty much the breakdown of an autonomous system, right? That autonomous system can be a missile, it can be a rocket, it could be a boat, it could be an underwater vehicle, it could be any of that. So a good way to explain what guidance, navigation, controls is that we're playing baseball, right? And we're all the way out in the field, and we're getting a ball hit to us, right? So what do? Put up our arm and try catching the ball. If we think about it and break that down into GNC tasks, what we're doing is we're actually giving our arm an angle. So we're actually getting an angle to each one of our joints within our arm to catch the ball. We can think of that as a trajectory that we're giving our system. Our system this time is going to be our arm. So that's something that would be a guidance task, right? And interestingly enough, if we have a ball up here and our arm can go like this, we can go like this, we can, double back and go like that. So that's an optimization problem. So a lot of times your guidance is going to be formulated as an optimization problem. So what kind of senses are we using when we catch this ball? Sight, right? So we have some kind of visual sense of where this ball is at in that point in time. Anybody, any other sense that we're using? So there's actually a sense that they don't talk about. When they talk about 5 senses of the body, we actually have something closer to 8.
Perception, distance perception.
Yeah, so we could use stereoscopic vision. We'll classify that under vision. But your body inherently knows the position of your joints, regardless if you have visual feedback or if you lose your sense of touch for that limb. So you're actually able to know the angles that your joints are at. And also we're using our sense of touch to know that we've caught the ball. Right? So all these sensors get bundled up into a package, and that's kind of like the navigation system for that task, right? So we're using these sensors and we're filtering it in our brain to actually be able to catch this ball in midair, which is an extremely complex task if you think about it. That ball is probably going at what, 70 miles per hour? And your arm's moving at what, a few meters per second? So it takes a lot of foresight to be able to actually catch that ball. So that would be like navigation, which would be all the sensors and filtering that takes place for us to have something called feedback. So there's a lot of popular sensors, accelerometers, gyroscopes, magnetometers, DVLs. All those sensors are what you guys are using in your projects. And if we go back to our example and we talk about control, control is how we pull and push our muscles to actually achieve those desired angles that our guidance system is giving us, right? So control is all the actuator inputs needed to follow a reference trajectory from the guidance. And we use the feedback from our navigation system to do that. So in this slide, I just have a pretty quick summation of what you would do in like a maritime environment. You guys know what on the bottom left-hand corner what those are? So we got we got 2 sensors. What are those? Compass, and what's the second one? Gyroscope, right on. So with those, what are we able to measure? No.
Direction.
We're able to get our bearing and
Attitude.
yeah, so it would be our attitude and our rates, our angular rates for our body, right? So with the gyroscope, you're typically able to get your z-axis rate. If it's a nicer gyroscope, you're able to get a 3-axis rate for your x, y, and z axis, right? So our guidance system would be like feeding in a series of waypoints, and then our navigation system would be getting in our compass, our bearing, and also we would have some kind of GPS system to be able to get our position. And what we do is we perform an operation on the guidance navigation to give us an input to our control system. And that input's going to be the system here. Then our control system will provide inputs to our actuators. So I'm going to do a couple of some introduction vocabulary. So a system is a process that evolves over time. If we think about the entire universe, our system is a subset of that, right? And there's all these little holes that you can actually poke in from the outside universe to our system. And those are the inputs. And then our system has some kind of effect on the outside universe, and that will be our output. Right? So it sounds like the majority of you guys have taken dynamic systems, so you're familiar with what a system is, or what a dynamic system is, right? So it evolves over time. A plant is the model of interest that relates its input to its output, and its output is a measurable effect produced by the system. The state is the minimum number of variables that completely describe all of a system at a certain point in time. Right. So we can have a bunch of variables to describe our system, but not a lot of them are going to be meaningful, right? So if we're running around CTEC with VBAS and our temperature sensor inside our control box is reading something, that can be considered a variable, but it's going to have no output. It's not going to have any effect on our output whatsoever, right? Unless we're trying to do some crazy closed-loop thermal control to make sure it's going under some kind of shade to make sure that doesn't exceed some certain performance requirement. So let's not worry about that, right? So we got to think about the minimum number of variables that can completely describe a system at a certain point in time. So how many of you guys have worked with VBAS or the underwater vehicle? A few guys? All right. So out of you guys that raised your hand, what are some of the states that you have to deal with?
Mission state, like high level, I mean, what task we are in currently, what we're trying to do.
So the state relates to the dynamic system itself.
So for that, then it's
Heading? Okay, that's good. Any other states? Position, right? So you have your X and your Y position and your heading. So you have 3 states. Those 3 states are what we call your kinematic states. Now you also have 3 more dynamic states. Do you guys know what those are? Your speed, right? Your body velocities, right? So you have 2 linear velocities and you have 1 angular velocity when you're dealing with surface vessels, right? You have your surge velocity, your sway velocity, and then your yaw rate. So surge is bow, sway is starboard, and then your yaw rate is how you spin from X to Y, right? Because we have a Z-axis positive down system. So that's something in a marine vehicle. It'll be a surface vehicle. Underwater vehicle, you'll actually have 6 kinematic states and 6 dynamic states, right? Because at that point, you have to operate in full 6 degree of freedom space. With a surface vehicle, you're kind of constrained to work on like a plane, right? So if we think about the table as a plane, we can only really go forward, back, left, right. Can't go down, we can't go up. We can spin around though. When we're working with a 6 degree of freedom system, it would be like us, so we're able to move up, down, left, right. And we're also able to change our orientation in 3 ways, right? So it'll be how much we roll about our x-axis, how much we pitch about our y-axis, and how much we yaw about our z-axis. So feedback is the connection between a system's output and its input, right? So we don't have control without feedback. We have open loop control, which is okay. Can't really get it to behave the way you want it to with open loop control. And that takes a lot of knowledge of the system to actually be able to get it to reach a steady state that we're trying to get with open loop control. And so I said open loop control, so let's define it. It's a plant with no feedback, but that doesn't necessarily mean that the inputs are 0. So these are a couple examples of control systems. The first real foray into control systems was through Boeing when developing autopilot systems. Autonomous vehicles have extremely advanced GNC systems associated with them. Rockets are an example of inverted pendulum, right? So it's an inverted pendulum in air that we're trying to keep upright to make sure that we can get it up into space. Everybody here who has a computer is running some kind of control system within their computer through something called phase lock loop control. So we have some kind of oscillator going into our processor. We have some kind of output from our processor that's also an oscillation. What we're trying to do is we're trying to match the phase between our input and our output. What that means is that whenever we have an input that's a rise, we also have an output that's a rise. Active vibration control, so anything that has an earthquake-prone building. There's a lot of passive dampers that are used. But now that we have the technological power to be able to design active control systems, you're actually able to design systems that will either move the center of gravity of a building as it's swaying to minimize structural impact. And surprisingly, control systems aren't a man-made occurrence, right? They happen all the time in nature. So how many of you guys are familiar with a concept called homeostasis? You guys heard it before? So everybody knows, right? So that is our body trying to achieve something called a set point, right? So 98.7 degrees is your body temperature, and that is a set point that our body's trying to reach. So it has all these processes that are trying to keep our body temperature at that level. Heart rate, 90 beats per minute, 80 beats per minute. Blood pressure, 120 diastolic, 80 systolic, right? So all these are control systems that occur within our body. They're not as pretty as man-made control systems, and the way that they're actually able to actuate to get to those levels is much more complex, and it's actually quite difficult. It's actually quite difficult to imagine how a system like that could just occur. So it's not just the human body, though. Even the smallest cells undergo some kind of control system. So there's something called the potassium-sodium pump. And 25% of a cell's energy is devoted just for this control system where it's pumping potassium and sodium in and out of its cell. And what it does is that it actually controls the volume of the cell itself. So 25% of all the energy that we consume is being used by a control system. So not only are control systems everywhere, they're the reason we're able to think and do the things that we're able to do, right? So this is an extremely, extremely important subject. So, and like I said before, stability is the most important subject in controls. So let's do a pop quiz. Bottom left-hand corner, what is that? What kind of stability? Is that stable, unstable, or something else? So we have a ball that's on top of a hill. What happens if a wind comes over and picks it up? Unstable, right? So that means that ball will roll off. So what about the middle one? Is that stable or unstable?
Unstable.
Unstable. It's actually marginally stable. So if a wind picks up the ball, it moves, then it moves just a few feet, and it stays there. Does that sound familiar to you guys? Maybe if you got a boat and you're spinning it, it doesn't bounce back to that heading, right? It just stays there. Or if you got a boat and you just give it thruster commands, it goes, and then it just stops at that part, right? So that's a marginally stable system. Is it good or is it bad to have a marginally stable system?
It depends.
That's exactly it. It depends. So sometimes it's fine for you guys to have a marginally stable system. Sometimes it's very bad to have a marginally stable system. So sometimes our marginally stable systems will just display that kind of behavior that I talked about, where they go from one position to another and stay there, which is fine because it's not going to break anything. Or sometimes marginally stable systems will drive your system to oscillation. Those oscillations can cause damage to the machinery operating it, right? So the last one, by process of elimination, what is that? Who can describe to me why that is a stable control system, or why that would represent a stable control system? The wind will move it. You're right. It's got shelter from the wind.
But if you roll up the hill, eventually it's going to get back to that state, right? Even if it may go up on one side, go up on the other, it's going to continue to get lower and lower until it comes back to that state.
Exactly. So we have friction operating on it. We have air resistance operating on it. We have all these forces that are doing what? They're maintaining balance, but more importantly, they're taking energy away from the system. So controls, the very essence of control systems is that you're inputting energy into a system and you're taking away energy to a system. So you're dictating when you're going to put in energy and when you're not going to put in energy to a system. And that is what is the difference between your pendulum that starts oscillating all over the place and eventually breaks itself, or the pendulum that nicely rights itself up. Once you have a pendulum that nicely rights itself up, it's only a few more steps until you have a walking robot. So mathematical foundations, how are we doing with complex numbers? Kind of, okay. Ordinary differential equations with Laplace transforms. We've taken, was it Dr. Madani's dynamic systems course? Dr. On's dynamic systems course. That's a good course. I like that course, yeah. How about block diagrams? You guys know what I mean by a block diagram? Right, okay, that's fine. So I guess I'll do a quick example on imaginary numbers. Shot my guy. What is the variable that we use to represent a complex number? I. That's an imaginary number. So a complex number is a summation of a real number with an imaginary number.
Z.
We almost always use z, right? So z is equal to x plus iy. Right? So if we look at a complex number plane, what's the x-axis?
Real axis.
Real. X. What's the y-axis? Correct. So I'm going to use a substitution of variables to make this more similar. Maybe you guys are going to recognize this. So instead of z, I'm going to use s. Instead of x, I'm going to use sigma. We can use I or j if we're talking about imaginary number. For imaginary number, we can use I or j as a notation. I'm going to say y is omega. So now our system has gone from z xy to s sigma j omega. Right? The cool thing about this is that we can represent any complex number in this plane, right? So we can represent it as a vector. So if we say that s is equal to 1 plus 2 j omega, or omega, we can go 1 here, 2 here, here. Right? So s is equal to 1 plus 2j. So this is a vector in a space. If this is a vector in space, we can get a magnitude out of it, right? What's our magnitude?
Square root of the sigma squared plus omega squared.
Exactly. So if we want to talk about the magnitude of S, that is sigma squared plus omega squared. We can also talk about an angle here. Phi. What's my angle?
Tan inverse of omega over sigma.
Exactly. People are scared of complex numbers. There's no reason to be scared. They're very simple, right? So we can actually pretty much talk about complex numbers very easily using the imaginary plane. So what happens is when you perform some kind of Laplace transform, which I'll get into right now, that actually uses this S term. So we use a transform that uses S is equal to sigma plus j omega. Is there an eraser here? Any chance?
I don't think so.
Napkin? All right, that works for me.
There's maintenance too.
Got some water. That'll be fine. Are we okay with complex numbers? You guys want me to go over anything else, or we're doing all right? Are you bored? You guys already know all this.
Yeah, we have a quiz on complex numbers next week, so
Okay.
this is helping us.
Everybody wants to be model.
That was useful though with the sigma and omega though, because I haven't seen it that way.
Oh, okay.
Yeah,
For sure.
Like obviously I know what the complex plane is, but not with those particular variables which apply to systems. I understand, right?
Yeah. So I'm going to talk about Laplace transforms right now. Why do we use Laplace transforms?
You use it to filter out noise too.
Exactly, right. So, yeah, you can use it to filter out noise as well.
Well, it's determined where to.
Yeah. So you use that to design your low-pass filters, right? So that brings up an interesting point. Have you guys ever taken any kind of signal processing course? No?
Yeah.
So control systems and signal processing are two sides of the same coin. As controls engineers, you're often tasked with designing filters for your system, right? So you got to know some signal processing. And the actual design of signal processing and control systems are nearly identical. So they're really just two sides of the same coin. And if you're designing a type of something called an infinite impulse response system, that is completely analogous to a continuous linear time invariant control system. So we'll start off with a Laplace transform. So we signify our Laplace transforms usually by some kind of uppercase letter as a function of S, right? And S before is equal to sigma plus j omega. Right. So we say that f of s is actually the Laplace transform of some function f of t. And that is equal to, who knows this? It's an integral from where to where?
Negative infinity to t.
Close. From 0 to positive infinity. This is something called the unilateral transform, which is equal to our function f of t times e to the negative s t dt, right? So as a quick aside, I think I'll do it over here. We have this, right? It's from 0 to infinity, e, or f of t times e. We're going to break down s into its components. So it's negative sigma of t times e to the negative I, or j omega of t dt, right? What happens if we set sigma to 0? Does this look familiar to anybody? What is that?
Fourier transform.
Exactly. It's half a Fourier transform, right? So Fourier transform would be from negative infinity to positive infinity. This is a unilateral transform from 0 to infinity. So you can see that just by setting our sigma term to 0, we're actually able to get the Fourier transform of our system. So we have this transform. What if we want to find the transform for the derivative of this, right? Does anybody know what that would be? take the operator out? We can't take the operator out. So there's actually a solution to the derivative of this equation, right? So it is s times f of s. So this would be our original function that we're not taking derivative of. S times f of s minus f at 0. Are you guys okay with that? Okay.
And that's little f at 0 there?
Little f of 0. So we're talking about the initial condition for that f of t term. So by that, let's say that we have some kind of function g of t. G of t is equal from 0 to t of f of t dt. So what is the Laplace transform of g of t? By that same logic, so if we're multiplying a function times s for our derivative, and we know that derivative and integrals are inverse operations, what would you imagine our Laplace transform of g of t, which is the integral of f of t, would be? It would be f of s
Divided by s?
divided by s. Right. So if we have our boat, we've got an acceleration, we feed that into one of these, what do we get out of it? This is our acceleration. We're integrating it. What do we get? Velocity. Correct. Integrate that one more. What do we get? So this is a gross simplification. This is only true for one dimension, but that's basically to hammer home the point that 1 over s, all that is you're integrating the system. When you're multiplying times s, all you're doing is taking the derivative of the system. Right? So we use Laplace transforms as a way to give us a shortcut into solving out a system. Right? So right. So luckily for us, we don't need to solve out any of these integral terms. They've already been solved out for us, right? So we know the Laplace transform of sine of at is equal to a over s squared plus a squared. What's the Laplace transform of x double dot? Of the second derivative of x?
X squared, x.
But we also have our initial conditions that we have to worry about, right? So we saw what was for one derivative. So for second derivative, we have minus s
Y prime.
x
or
dot,
X prime.
right?
Minus.
Minus x dot 0, and that's going to be equal to the Laplace transform of this, which is
Omega over x squared plus omega squared.
Yep. So now we want to solve out for x of s. So x of s is equal to s x naught over s squared, cancel these out, plus x dot over s squared plus omega over s squared plus omega squared. Right? So we have the Laplace transform for this guy, 1 over s. Yes, that is just a constant. So this is known. We have Laplace transform from 1 over s squared. So this is known. So remember that we're dividing by s squared. So there's an s squared here. Do we have a Laplace transform for this guy? No. So we actually have to do something just through algebraic manipulation that'll get us into a form where we can find an inverse Laplace transform for this. So what do we do? So this is this over s squared plus omega squared times s squared. Do you guys remember partial fraction decomposition? Barely? Kind of. I always have to look up the rules to it every single time I do it. There's just, I cannot remember it because it's one of those things where you'll see every once in the blue moon.
Yeah.
So that is equal to AS plus B over S squared, because our denominator, or excuse me, our numerator is always 1 degree less than our denominator, plus CS plus D over S squared plus omega squared, right? And we solve this out. How do we solve that out?
Don't you also need an S in the denominator, another term?
Where?
Because normally when you have, well, I guess that is an irreducible quadratic, but normally, like if you had like s minus 1 squared, you would need s minus 1, the whole thing squared, and another term for s minus 1.
So we actually don't need that because we're not squaring an entire term.
Okay,
Yeah.
true.
So we could solve this out if we brought in complex numbers, but I don't know if you guys deal with inverse Laplace transforms with complex numbers just yet. But yeah, that would be correct if we wanted to solve this out using complex numbers. You would end up with exactly the same solution. To this
Okay, it would just be a lot longer and more horrible.
Not horrible. Complex numbers are easy. So I've already done this out, but you guys want to multiply both sides by the denominator, and then you end up with some kind of expression. And you want to relate each degree of your polynomial on the right-hand side that we have here, the left-hand side. So we're going to end up with something s cubed. That s cubed term is nothing on the left-hand side, so that's 0, s squared, 0, s, 0. The only thing we have is on the 0th order. And our solution comes out to be a is equal to 0, c is equal to 0, d or b is equal to 1 over omega, and then b is equal to negative 1 over omega. So what we've done is we've essentially split this into this, into 1 over omega s squared times 1 minus 1 over omega squared, omega over s squared plus omega squared, right? So now we are able to find what inverse Laplace transform for this equation. What we end up getting for our solution is that x of t is equal to x naught plus x dot naught times t Do you guys have too many questions and are embarrassed to ask? Okay. I'm here. I love dumb questions. That makes my job so much easier. The hard questions are the ones I don't like. All right. So I got another hour and I got like 50 more slides. So I'm going to breeze through these. Okay. Second order system. What's a second order system? Do you guys remember what a second order system is?
No.
Okay. That would be something like we just solved out. That would be a system that would have two kind of differentiations. Two differentiations in there, right? So we'd have to up to the second derivative of our x term. So the most common system of controls is a second order system. So it's a system with two derivatives of its equation of motion. And if you're a mechanical engineer, that means the mass spring damper. Or do I have any electrical engineers in the room other than Raul? Nobody? Then that's an RLC circuit, right? Those will give you exactly the same kind of something called a transfer function, which I'll get into in a second. So why are second order systems important for control systems? Does anybody know? Right. So the second order system, oftentimes when you're tasked with designing a control system,
Special guest.
hey,
Hey.
how's it going, man? Oftentimes when we're tasked with designing a control system, we want it to behave like a second order system. The question is, why do we want it to behave like a second order system? The properties for second order systems are extremely well known. So performance metrics are easy to design given certain parameters, and you'll often find that higher order systems will often act like second order systems. So I mean, if you're designing like rockets and stuff like that, you're talking about systems that can go up to the 14th order, right? That means 14 derivatives. It's awful. But what you'll see is that oftentimes you can actually say, well, this is kind of negligible. At this point, this is negligible, this is negligible. And your system can almost behave like a second order system, right? And you'll see that has to do with something called the poles. I'll get to that later. Mass spring damper. We've seen this before, right? Vibrations class with Dr. Glegg, Madani. Who's teaching it these days? Glishikov. No? Okay.
Next enough.
Thankfully.
Okay.
Everyone's tough.
They do some of that in dynamic systems on.
Yeah.
Installed out.
And we actually did RLC and EMD as well. Like, that's where I learned about like the overdamping, underdamping.
Yep. That's exactly it. So RLC circuits go through the exact same thing that mass spring damper systems go through, right? It's just easier to talk about mass spring dampers when it comes to position than when you talk about, I think it's charge, that's your state for an RLC circuit. I'm not an electrical engineer, so I don't know.
Wow, yeah.
So we have a mass and we have a spring given by the squiggly line, we have a damper given by the pot, right? So springs store energy, dampers dissipate energy. Every system that you work with can be described as a mass spring damper system. There is not a single system that cannot be described by this simple equation. You might have several mass spring dampers attached to each other. You might have mass springs in several different directions. But for a certain neighborhood around a certain state, your system will behave like this, right? So this is why we always start off with mass spring damper systems. I know when I started off with dynamic systems, I had no idea why mass spring dampers were that important, right? But it turns out that we're engineers and we love approximations. And most systems that we work with are nonlinear. What we can do is we can use a Taylor series approximation to get that system to be linear around a certain operating point, right? And when it's linear around that operating point, guess what it is? A mass spring damper. So we have one force for our spring. We have one force for our damper. We have our spring force to be our spring constant K times our position X. And we have our damping force to be our damping constant times our velocity. And we know from Newton's second law of motion that force is equal to mass times acceleration, right? So we're talking about a single degree of freedom with X. What that means is that we take two derivatives of X to give us our acceleration. So mass times the double derivative of X is equal to our spring force minus Kx plus our damping force minus Bx dot. We solve that out and we get it all onto the left-hand side of the system, which is equal to 0. Does anybody know what a system like this is called when it's equal to 0?
Homogeneous.
Homogeneous, correct. Yeah. So we have a homogeneous system in this case. So what I'm going to do first is I'm going to solve this out for the undamped case where B is equal to 0. So let's see predictions here. What kind of system is this going to be when B is equal to 0? I hear unstable. Anybody else got another guess? I hear marginally stable. Anybody else got stable? So I hear unstable and marginally stable. Okay, we'll find out. So we go to our buddy Laplace and we perform a transform on that system, right? We go in, we solve that out, and we get our equation that relates x of s is equal to x naught s over ms squared plus k plus x dot not plus, or excuse me, over ms squared plus k, right? And we solve this out, we divide by m, and what we get is this highlighted equation for our system, right? So we already know kind of how our system is going to behave, right, from looking at this equation. We know that it's going to oscillate at a certain frequency. What is that frequency that it's going to oscillate at? Correct. Does anybody know what that's called? Absolutely. So this is the natural frequency of our mass spring damper system. What happens if we're trying to approximate our rocket as a second order system? Is there going to be a natural frequency associated with the rocket? You bet you that's going to be there. So all this stuff that we're talking about mass spring damper systems, it's going to happen in all the systems that you're trying to control with, right? So we know we have this equation. From the equation above, we can see that there is an undamped frequency of omega n is equal to radical k over m, which is our natural frequency. This is called a harmonic oscillator. Who knows how this is going to look like in time, right? Do you guys know how this is going to look like in time? Sine wave oscillation, that's all it is, right? So, going back and thinking about this, what kind of system is this? Unstable, marginally stable, stable. It's a marginally stable system because it's driven to oscillation. The oscillations are not dying off. So if we think about our pendulum swinging back and forth, what happens if we have nothing taking energy away from that system? It'll just keep on swinging back and forth, and we have a marginally stable system, right? So the difference between marginally stable systems and stable systems is that you have some kind of component dissipating energy, which acts like a damper. So let's talk about the damped case. What happens when B does not equal 0, right? And because I didn't feel like driving out a whole bunch of equations, I said that our initial position is equal to 0. So we have this solution for x of s in the Laplace domain, which is mx dot naught over ms squared plus bs plus k, right? So just reviewing, what's k? What's b? What's m? There we go. So there are actually several solutions to this problem dependent on the parameters of the denominator, right? Depends on the roots of the denominator, also known as your poles. So, how many of you guys remember the quadratic formula from Algebra 1? We all should, right? So it's minus b plus or minus the radical b squared minus 4ac over 2a. That's drilled into our skulls. Why is it drilled into our skulls? Because it's useful. Because you'll come up with situations like this where you have to solve out and factorize some sort of polynomial, right? A second order polynomial. So we get the bottom equation, right? What happens here is that we're big boys now. We can deal with imaginary numbers, right? So now we get several solutions that are possible depending on the value of b squared and 4mk, right? If b squared is greater than 4mk, we're good, we're in the clear. We're back to 7th grade algebra. B squared is equal to 4mk, awesome, even better. The entire radical drops out, we have to deal with just the square, right? We have to deal with some kind of polynomial that's raised to an order. But if b squared is less than 4mk, we have to deal with imaginary numbers. And what does an imaginary number look like in the S-plane?
What?
The S-plane. So remember that S is equal to sigma plus j omega. If we have an imaginary number, that means that we have an omega. If we have an omega, that means we have an oscillation. So let's go with the underdamped case first, right? So we're going to tackle the hardest one. If we solve out the problem, we get this solution. So what is this response going to look like to our initial velocity? So an initial velocity actually translates directly into something called an impulse. So let's say at time is equal to t, you give your system a big kick. That's exactly the same thing as having an initial velocity. So we see that there is a periodic response through the sine, right? We see that there's also a transient response around that exponential term, right? And it's an exponentially decaying term, which means that
it's going to oscillate to a steady state.
It's going to oscillate to a steady state, correct. And since we're only talking about initial push to the system, it's going to oscillate back down to its initial position, which in this case is 0, right? And you see that the difference between the undamped case and the underdamped case is that we're no longer oscillating at our natural frequency. Hey, how's it going, Colin? We're no longer oscillating at radical k over m. We're oscillating at the damped natural frequency, which is slightly less than that. So, Travis was absolutely right. This is the response of our system. And if you look at it, we look at that equation, we have an exponential term, e to negative b over 2mt. This is bounded by e to negative 2b, e to negative b over 2mt over here, right? So it is bounded on both sides by that exponential term. and it is oscillating at our damped natural frequency. Let's look at a critically damped case. What does this look like? So we have a T term here, and we have an exponentially decaying term here. So the question is, which one dies off first? So is this system stable or unstable? It would be stable, right? Because although this is going to infinity, this guy is going to 0. And anything times 0 is 0. So we'll see the response for that. And that response is actually identical to what you would expect for a first order system or something with just one derivative. Not identical, but very similar. So we have our initial push. Push goes up, and then it follows, and it is bounded by that exponentially decaying term. What about the overdamped case? Actually, I forgot to point out something. Take special note of how long the settling time is here, right? Talking about 8 seconds, right? So this is an overdamped case. We have exclusively transient responses here, right? Because what is sine of h? What's sinh? What's our sinh term? If we have sinh of x, what does that actually translate to? So sinh of x is equal to e to the x minus e to the negative x over 2. So this is purely an exponential term times another exponential term, okay, times some kind of amplitude. Similar shape to our critically damped, but take a special note at the transient response here, or settling time here. I'm talking about 23 seconds. That is a solid 15 seconds greater than our critically damped case. So I got a kind of a trick question for you. When we're designing a system, do we want it to be underdamped, critically damped, or overdamped?
Critically.
You would think that. We actually want it to be underdamped. A lot of the parameters are difficult to estimate, so it's extremely difficult for us to get precisely a critically damped system. With an underdamped system, you have a lot more leeway. Also, if you look at the underdamped system, we're able to get back to our starting position way quicker. Although it takes a little bit longer to settle down. So we're able to get a faster response to our system than an underdamped system. So when we design, we always want to have an underdamped system.
That has to do with that once your initial start is less improving back.
Exactly. Exactly. So we've been dealing with homogeneous functions. What happens if we introduce a forcing function and now we have an inhomogeneous response, right? So what we had before was that mx double dot plus bx dot plus kx is equal to 0. Now we have a forcing function in its place, right? So we do a Laplace transform, and we're control engineers and we're lazy, so we stop there. We stop at the Laplace transform. That's all we need. So we're left with this. What is this called? Does anybody know from dynamic systems? Right, so we have a transfer function, which is an input relating an output to the system. In this case, our input is our forcing function, and our output is our state, x. So second-order systems like the mass spring damper systems, when it comes to the transfer function, are often represented by this transfer function, right? This transfer function is nice because it gives us a lot of properties of our system that we like. We have our natural frequency for the undamped system, omega n, and we have our damping ratio, which is b over 2 times radical mk. So we're actually able to describe our system completely through this transfer function, and it actually simplifies solving it out a great deal. And now we know exactly what our damped natural frequency is going to be, and we can see that's going to be just under, because for an underdamped case, we have a damping ratio between 0 and 1. It's going to be just below our natural frequency. So we have our natural frequency and our damping ratio. So all three cases, underdamped, critically damped, and overdamped, can now be parameterized by our damping ratio zeta. So zeta from 0 to 1, underdamped, zeta is equal to 1, critically damped, zeta is greater than 1, overdamped. So this is the same thing as an RLC circuit that some of you guys have taken in EMD, right? the most common forcing function is the Heaviside function, also known as the unit step response. Do you guys want me to go back a little bit? No? Okay. So this is the Heaviside function. It's often used to determine the performance of a system. So from t is less than 0, it is equal to 0. From t is greater than 0, it's equal to 1. Since our Laplace transform only cares about from 0 to infinity, that means that that Heaviside function is always going to be equal to 1 for us. So with this Heaviside function, we're immediately able to determine whether your system is stable or unstable. If it oscillates down to infinity, just like the pendulum that I showed you at the beginning of the lecture, you know that is an unstable system. If it slowly dies down, back down, we know that that is a stable system. This is also the basis for something called black box tuning of a system. So we don't know what the transfer function is for black box tuning, and we have to use something called Ziegler-Nichols first method. If you guys are ever dealing with a plant that you have no idea what it is, always look up Ziegler-Nichols and try doing what they're doing. I'm not actually going to get into it because that's a little bit more involved process, but that is the best way for you to get PID gains when you don't know what your system looks like. So for the underdamped response, this is what we get for our step function, right? So we have a nice buildup, we have a slight overshoot, and we have the settling time over again. And once again, it is oscillating at that damped natural frequency. So we can parameterize this by several different parameters. We have our rise time, which is from 0 to 100% for our case. Oftentimes, in a lot of other texts, you'll see that from 0 to 90%. In the industry, it's pretty much 0 to 100% all the time. You have your peak time, which is the time for you to go from 0 to your peak for an underdamped system. Then you have your settling time. Your settling time is the time in which your system remains within 1 or 2% of your reference input for the remainder of the time. We also have our percent overshoot, which is the peak response divided by our desired response, which in this case is about 20%. So the reason why second order systems are so useful to us is because there's a lot of empirical measurements behind them that can actually help us get our performance requirements and dictate what our system is going to look like. So what happens is that as controls engineers, you're going to get a whole bunch of performance requirements down from all sorts of people, right? So your system's going to have a certain rise time, it's going to have less than a certain rise time to meet performance requirements, you're going to need to have some kind of overshoot to make sure your system's not breaking itself. You're going to have some kind of settling time also to make sure it behaves properly. So we have all these empirical measurements that'll be able to give us an estimate of what the closed loop response of our system will look like. So what we have here is we have 3 equations and 2 variables. What is that called? As an overdetermined system, right? So that means that we might not have a solution for it. So we might not be able to get that system that has 1 second rise time with no overshoot, right? So a lot of controls is making compromises to see, okay, so we're going to have to take a hit on the overshoot to get the rise time we want, or we have to take a hit on the rise time to get the overshoot we want. It's often the case that you're doing something like that, right? So we'll do a Heaviside function input and a unit step response to all 3 of our systems. In the red, we have our underdamped system. In the blue, we have our critically damped system, and overdamped system in green. What you see is that the overdamped system takes quite a bit longer to respond to that input than the critically damped or the underdamped. And as you can see, the underdamped system takes the least amount of time to actually respond to that input. So what if I told you that we didn't even need to solve out these equations, right? What if I told you that just by looking at the transfer function, we are able to pick up the response of the system? That would be great for us, right? Cuts our work in half. So let's take a look. So we go back to our S-plane, right? So our imaginary S-plane. So on the x-axis we have our sigma, on our y-axis we have our j omegas. So the time response of our mass spring damper system is entirely dependent on the poles. What are the poles? The poles are the roots of our denominator of our transfer function, right? So our sigma for our roots of our transfer poles, the poles, the sigma is an exponential response, right? So that means that we have some kind of e to some other term. It's on the left-hand side of the complex plane. So if we have a negative real number associated with that pole, that means that it's going to be exponentially decaying. And then we also have an omega term. So if we have some kind of complex variable associated with our pole, that means we're going to have some kind of oscillation in our system. So if we look back here, we see that in red is the only system that we have an oscillation on. And if we look here, we see that the only poles that we have for that oscillation, the poles that have that oscillation are the only poles that are complex numbers. They also have a transient response because they have that sigma part to it, right? But they're going to have that periodic oscillation. And what happens is that if you look at the S-plane, we want our systems to behave kind of like second-order systems. And oftentimes we'll have more poles in our transfer function, or closed-loop transfer function, than the two that we typically have with a second-order system. So one thing to note is that as you make your poles more negative, the faster that transient response will go, and that term will die out. Right? So if we look at these poles, we see for the overdamped case that we have a pole that's all the way out by -3. That pole is going to die out much quicker than the pole that's going to be at -0.5. So our system, we can pretty much almost approximate it as a first-order system at 0.5, with a pole at 0.5. And one thing about the shape of these, right? So as we have an underdamped system and our damping ratio is less than 1, we're going to have complex poles. As we increase our damping ratio, we're going to see that the poles are going to coincide with a critically damped system. The critically damped system, we have two poles, but they're at exactly the same location. As we continue to increase our damping ratio, those poles are going to split, and they're going to start drifting away to the critically damped system here. Right? And this explains why we have a longer transient response with the critically damped system as compared to the critically damped system, or the overdamped system as compared to the critically damped system. Because this guy is closer to the origin on our S.
Can you explain what a pole is?
Sure. So a pole. No, the zeros would be in the numerator. The poles are in the denominator. So the poles will be the solution to our denominator term over here.
Oh, okay.
Those are going to be the roots. And if we go back even further, we see that when we solve down the quadratic term here, that's essentially what we were doing. We were solving for the poles of the equation. And those three conditions that I gave you are represented all in those poles.
You can just plot the poles like that, and then add a Laplace transform.
So you have to have the Laplace transform to actually get your system into a transfer function. Right? Okay. So you don't need to do the inverse Laplace transform to solve it out.
Okay.
Right? So, I mean, you should do the inverse Laplace transform to solve it out because the poles really give you the best representation for it. Your zeros will also affect the time response of your system. So your zeros would be the solutions to your numerator. You'll see that a little bit later in the example I put together. So right now we only talked about a unit step response, right? So what happens if we have some other type of response? Let's say we're trying to drive our system at a certain frequency omega, right? So we have our forcing function to be f of t is equal to a naught sine omega t, right? And what that means is now we have a solution. We now have a slightly more complex problem. What happens is when we solve this out using Laplace transforms, that we have a transient solution that's exponentially decaying, that is a function of your natural frequency. And we also have a periodic solution, which is oscillating at the driven frequency omega, right? Because if you think about it, we're trying to solve this out. We're doing x of t. What this guy does here is that means that we're going to have to do some partial fraction decomposition here. Right? We're going to split this apart. When we split this apart, we know that this is going to be in the denominator of one of our solutions, and this is going to be the denominator of the second solution. We already know that this is going to be exponentially dying out. This is left, though, as a periodic response. So we can actually generalize it, the solution to our system, as x of t is equal to a transient response of the system plus a steady state response. And as t approaches infinity, we only have that steady state response. So the solution of x of t as t is much greater than 0 would be the steady state response, which is equal to omega n squared 8 naught over the square root of omega n squared minus omega squared squared plus 2 times zeta omega n omega squared. It's a mouthful, man, but this is important because what does this tell you about our system? It's a lot of squares. But what does this tell you about the system if we look at the parameters? Does omega n change? No, that is an inherent property of our system. Does zeta change? No, that is also an inherent property of our system. So the only thing that can possibly change is omega, our driving frequency. Because we can change our driving frequency, what that means is we can actually change the amplitude of our system.
You got that just because the omega is the only thing being multiplied by the t? Or how do you determine that if these aren't changing?
What do you mean? Because well, when we start characterizing a system, we have a mass spring damper system. Your omega n doesn't change because your damping constant and your spring constant don't change. I'm sorry, your spring constant and your mass don't change. So your omega n stays the same. And then your damping constant doesn't change because your damping ratio doesn't change because your damping coefficient stays the same. Your spring constant is the same, your mass is the same. So those are all constants. The only thing that's a variable is your driving frequency, omega. But not only that do we have a change in magnitude because of omega, right? Because this is going to change your magnitude depending on what our driving frequency is. We also have a change in phase response. So there's going to be a phase response associated with the inverse tangent of our system. So let's simulate this out. So in the red, we have our input. In the blue, we have our output. So for very low frequencies on the top left corner, our omega is equal to 0.3 omega n. We have a slight phase shift, phase lag, and we have a slight increase in amplitude. As we approach something called our resonant frequency, we've all heard of resonance before, right? As engineers, we've all seen the picture of the bridge. The bridge, right, it starts oscillating at the natural frequency and it falls apart, right? So that's bad for us. So on the top right-hand corner, we can actually see that we have the resonant frequency our system's getting driven at the resonant frequency. And this is the maximum amplitude that you get, right? So as the washing machine, you load up your laundry, it starts spinning. Then you start hearing, right? That's when it hit its maximum response to the system. As soon as it starts going faster, you're going to see a die-off of that. So if we look at the bottom left-hand corner, we have that omega is equal to 1.5 omega n. We see that our response is slowly decaying. And then we have on the bottom right-hand corner that omega is equal to 2 times our omega n. And that you can see is even a smaller response. So we have a change in magnitude, and also importantly, we have a change in phase. The phase here is almost identical. Phase here, if you look at it here, it's about 90 degrees apart. The phase here, we're getting closer to about 180 degrees apart. And finally, as we get much, much further away from our omega n, we get a phase difference of 180 degrees. So from the previous example, we noticed a few things. The amplitude and the phase of the output for small omega is approximately equal to the input amplitude and phase. As the driving frequency omega approaches a resonant frequency, the amplitude increases, right? It's going to hit a max at the resonant frequency. And the amplitude is at max at the resonant frequency equal to omega r is equal to omega n times 1 over 2 zeta squared. So what happens if we plot the response of our system versus an input frequency? Right? We can actually determine the frequency response of a system just by examining the transfer function. So from the Laplace transform, S is equal to sigma plus j omega. We actually set sigma is equal to 0, and we only have j omega. So h of j omega, we solved that out. We got a real part, we got an imaginary part. So our magnitude is just the real part squared plus the imaginary part squared, taking the square root of. Then we also get some kind of phase change, which is just the arctan of our imaginary part over a real part. And lo and behold, it is exactly like the solution that we got before. So just by examining the transfer function once again, we can cut out the work of actually trying to solve the system. So when we plot the response of the magnitude and phase versus a driving frequency or input frequency to the system, we use something called the Bode plot. So how many of you guys are familiar with logarithmic scales? Right? We're all familiar with logarithmic scales. We use a logarithmic scale to denote our frequency, so we have a broad range of frequencies that we're able to look at. We also use a decibel scale for our magnitude. We use a decibel scale for magnitude because of a little trick, right? So 20 log of AB is equal to 20 log of A plus 20 log of B. So if we're multiplying two things in our system, right? If we're multiplying A times B and we're taking the log of that, that is exactly equivalent to us taking 20 log of one of our multiplication systems, 20 log of A plus 20 log of the second system we're multiplying by, B. So that gives us a nice, easy way to actually represent the magnitudes of our system. We can just add them together versus trying to solve out the entire system. And this plot is called a Bode plot, right? So what we have here is the frequency response radians per second on the x-axis. So this isn't logarithmic. This is at 1 radian per second, 0.1 radian per second, 0.01 radian per second, right? Likewise, we go all the way up to 100 radians per second at the other end of the axis. So what we have is we have pretty much what we saw before, which is the same response or our magnitude until we hit a certain point here, and then we see the decay. And this graph doesn't really show it that well, but if we zoom in here, we actually see that there's a peak right here, and that corresponds to our resonant frequency. Same thing with the phase. If we take a look at the phase, we see we get a cutoff here at about 1 radian per second. If we take a look here, we see that our phase drops off about 1 decade before, 1/10 of our cutoff frequency here. So, because it's a second order system, and just like the time response of a second order system, we have really good empirical measurements for our second order system, for something called a bandwidth. So a bandwidth is going to be from 0, it's going to be pretty much the frequency between 0 and negative 3 dB of our system, right? So the response here for a bandwidth would be from 100% down to about 70% of our system. And that's equivalent to our bandwidth. We can determine our peak amplitude solely as a function of our damping ratio.
I have a question.
Yes, sir.
So let's have a system, and I apply a force to it, and the force that is acting by my Bode plot is basically a response. So the bandwidth that you have is an omega.
So the force, you're driving it at a certain frequency, right?
Right. So if I remember on the equation, I have omega and I have damping coefficient. I'm talking about that omega that is basically related to the force on my driving. So when you say the bandwidth, we're talking about that force that follows in that frequency. It's being behaved.
Right. Exactly. So within your bandwidth of your system, it pretty much whatever input frequency you have, you're going to get the output frequency. Right? So this is, I took a class with Dr. Maestri. This is a really good analogy. So you're a boxer, you're Vander Holyfield in the 90s. You're wrecking everybody. So what happens is that you're punching the guy in front of you. Punch him. And you keep on punching him at this rate. His head is bobbing back and forth at that rate. It might lag behind a little bit, but depending if you punch him faster, his head's going to keep on bobbing back and forth. You punch him even faster, it's going to bob very, very little back and forth, right? So that's kind of the analogy that he explained it with. It's always stuck to me because it's wild.
I'm translating right now.
So we see that after what we call our cutoff or corner frequency at the negative 3 dB, which is equivalent to our bandwidth in the second order system, we have a negative 40 decibel per decade drop off. So mass spring damper systems are now second order systems. We also deal with first order systems, which look like this, which is a first order low pass filter, very, very simple system. Perform a Laplace transform. We get down here to inverse of the Laplace transform 1 over tau s plus 1 times our input. And if we solve this out for step function, we get x of t is equal to 1 minus negative 1 over t, or negative 1 over tau times t. And the transient response, the time response of our system looks like this. What does this look like to you guys? Looks like either a critically damped system or a over-damped system, right? That goes back to that pole that it starts behaving like the first order system when you get that pole closer to the origin. So this is really nice about a first order system. When our t is equal to our time constant tau, which in this case is 1, our response is 62.3% of our max response, always, period. Another nice thing about it is that our settling time is nearly always, or actually it is always 4 times our time constant. And if we look at the frequency diagram, the Bode plot, this is very similar to the Bode plot of second order system, except we do not have a peak. There is no resonant frequency in a first order system. We only have a nice drop off. Our bandwidth in this case is equal to our time constant, and our drop off here is at negative 20 dB. So for second order system, we had a drop off of negative 40 dB per decade. For first order system, we had a drop off of negative 20 dB per decade. What about a third order system? What do you think the drop off for that would be? Negative 60 dB per second. Fourth, 80. And you keep on going. So whatever the maximum system drop off you have, it's going to be 20 times whatever the order your system is going to be the drop off. So if you're designing on like a Butterworth low pass filter, who knows what I'm talking about when I say that? Kind of. Yeah. Exactly, right. So when we're trying to do a Butterworth low pass filter, you typically will design for like the 7th order, right? And then depending on what kind of drop off rate you have. But they have a little bit different frequency response. So we're back to block diagrams. This is the fundamental representation of control systems, right? So what we have here is we have a reference getting fed into this block. What is this block? Summation block. We get our filtered output through our sensors. What is this? So we're using our summation block from our reference and our output to get our error. We're feeding our error into our controller. Controller is providing an input to our plant, which is providing a output, which is getting fed back through our sensor model, which gets back into here. Right. What happens is that we have a transfer function that relates this entire closed loop system. So we have y over s, y of s over r over s, which is equal to our controller times our plant over 1 plus our controller times our sensor model times our plant. This is very important because what do we know that determines the stability of our system? What do we know that determines how our system behaves in a time response? We always know about our poles, right? So our poles determine everything about our system. That is why we classify or we call the denominator of our closed loop transfer function the characteristic equation. So it's 1 plus our controller times our sensor model times our plant. So this would be like an example. We have some kind of reference getting fed in. We have some kind of error. That's going into a PID block, producing an input, which is going into a second order system, which is our plant, which is producing the output, which is getting fed back into our sensor model, which in this case, oftentimes, it's a low pass filter. 1 over tau s plus 1, which gets fed back. So the poles and zeros of our transfer function are dictated almost entirely by the PID controller block, the plant, and the sensor model. And stability is determined through the characteristic equation, of course, right? So we have to look at the denominator of the closed loop system. So if we think about the exponential response, that transient response, sigma of our S term, we know that it has to be on the left-hand side because we want that to be exponentially decaying. If it's on the right-hand side, what is it then? Right. It's exponentially increasing, which is bad. So on the left-hand side of our S-plane, we have stable systems. Any system on the imaginary axis or on the origin is marginally stable. Any system on the right-hand side is going to be unstable. Right? If we go back to our actual ball analogies, this is how it breaks down, right? So we have the valley ball as a stable system. We have a marginally stable system as the ball that just remains on a flat plane. We have an unstable system as the ball on top of the hill, right? So any positive poles in our system will drive our system's instability, just like that. Right? Have you guys heard the controllers joke before? Okay. So there's a plane flying out of Poland, and it starts shaking really bad, and the pilot goes on. Pilot's an old control engineer. He says, "Quick, everybody, get on the left-hand side." I heard that at a conference of the highest minds in controls.
Did you boo?
I don't have enough pull to boo. Or trust me, I would have.
They don't get out much.
So if we look at the time response of our system, we have a stable system, so we have that nice rise to a set point. Marginally stable system, we have that constant oscillations, and we have an unstable system, which is that exponentially increasing response, which in this case is driving to 10 times 10 to the 25th in 20 seconds. So that's real bad. Real bad. All right. How are you guys following me? Okay? More or less? Good? All right. How many of you guys have worked with a PID control block before? Or control? Any kind of PID controllers? Proportional integral derivative controllers? No? How much time we got? 20
All the
minutes.
time you need.
I got a meeting, so I can't. Okay. All right, so of you guys that worked with a PID controller block, how would you describe it?
Well, you have a proportional and integral and derivative term.
Right.
And by tuning those gains, the Ki, the Kp, and the Kd, you can dictate what your time response is, what your overshoot is, and what your settling time is.
Yep, exactly. So the PID controller is a way for you to control your system. It is a type of controller. So you have a proportional term, Kp, you have an integral term, Ki, and you have a derivative term, Kd. And these all relate to the error in your system, right? If we go back to our block diagram, right, what's getting fed into the PID controller, that block right there, is that error in our system. It is the output from our sensors. So it is the reference minus the output from our sensors. So PIDs are the most widely used controller type ever. We might modify it a little bit depending on the case, but well over 50% of the controllers that are in use right now are PID controllers, right? So why are they so prevalent? They're simple and they're robust, right? So there's three terms that use to dictate the performance of the system, which is Kp, Ki, and Kd. And it's robust to low frequency disturbances and unmodeled dynamics, right? So a lot of times it's difficult for us to model our systems and there's going to be inherent inaccuracies in those models. PID, especially with an integral term, is able to account for that. So the proportional gain responds immediately to the errors within the system. And that's dependent solely on the magnitude of the error. So if you have a small error, you have a correspondingly small control force. And it acts like a spring in the system, right? So it stores energy. We have an integral term, and what the integral term does, it is used to minimize steady state error. So large values of Ki may drive the system to oscillation and affect settling time. Then we also have the derivative gain, and that responds to errors before they happen and acts like a damper in the system. So you'll actually slow down the system a little bit. So with a derivative gain in the system, you'll actually slow down the transient response. But as a compromise, as a benefit, you'll have a smaller overshoot, right? So with PID control, you can actually use any combination of these. You can have just a proportional gain, you can have a PI gain, a PD, ID, IP, right? And they all look a little bit different. So I'm going to draw these for you right now. So let's talk about our unit step response, right? Our heavy side friction. So we have the time response of our system, we have our time. And we wanted to get at a steady state value, which we're going to call 1. So our proportional gain is actually going to look kind of like this. This is just a peak control. You're going to have some oscillation, and then you're going to have something called a steady state. This is kind of a dumb control system, right? So all we're really doing is just multiplying our error times a number, right? So we can't expect it to have the best performance that we really want. So we're going to have a high overshoot. We're going to have some oscillation. Our settling time is going to be great. We're also most likely going to have some kind of steady state error associated with our system. We can actually make that a little bit better by incorporating a PI term. So we're going to do an integral term. What happens here, now we're going to have a faster response, but way more oscillation. But no steady state error. So we include this integral term because that integral term will actually kill out our steady state error as our time goes to infinity. But we also have a faster rise time, which is good, but we have a larger peak. We're going to have a longer settling time as well. And then we can add a D term. So we're actually going to increase the transient response, less overshoot. Settling time can stay about the same. So with the PID, we can kind of get the best of each one of the controllers, right? But it does come at an expense because it becomes a little bit more difficult to tune, right? With a P controller, there's lots of approaches that you're actually able to tune with the P controller. How many of you guys know what a root locus plot is and how to tune a root locus?
I remember vaguely.
Vaguely, yeah.
When you have two poles, you have to point towards it, and if it's in between, it's not good. Somewhat.
So yeah, it kind of it's a lot easier if you just use RLocus on MATLAB. At one point in my life, I knew how to do it by hand. But a root locus plot is basically a way for you to tune a single gain in your system. So with that single gain, you actually see where your poles are for your open loop system. And it's interesting that it's only about 60 years ago that we proved that your poles, as your gain increases, are driven to the zeros in your system. So what happens for a root locus plot is that you have a diagram with the poles, and it has a trajectory of where your poles will be as you increase that gain. And as k goes to infinity, they will actually either hit negative infinity or positive infinity, or they'll hit a 0. Right? So with that, you can actually set what your closed loop poles will be. Right? As controls engineers, that's what we want to do. We're playing around with poles all day. Right? So typically, from our performance requirements, we're able to derive what our pole should look like. From deriving what our pole should look like, we can look what our characteristic equation would be like, and then we can actually tune those gains appropriately. Or we can use PID tool and let MATLAB do that for us, right? So with PID tool, you'll be able to pretty much take in any system and just tune it as you'd like. So each one of these gains has some advantages to it, but it also has a number of disadvantages to it as well.
So it might take a minute.
Yeah, it's got to heat up the lamp. So a proportional controller directly decreases our rise time. It directly increases our control bandwidth. A large KP will minimize our steady state error, but it'll never do away with our steady state error. We're going to have to live with that steady state error. So we typically will add on an integral term to cancel that steady state error out. So there are some disadvantages to a proportional control. It's that it amplifies the noise at all frequencies. So if you have some kind of disturbance that happens at a larger frequency that you're really interested in, that will affect your system. It also decreases something called gain margin. And gain margin is a measure of robustness to our system. So if we have a really high gain, we will have a less robust system that's able to handle less inaccuracies in some cases. Some cases it's the exact opposite. Bear with me. So an integral gain, that eliminates steady state error as t goes to infinity. Right? So small uncertainties in the plan can actually be accounted for, but it produces an aggressive response at the low frequency. So that's pretty good if you're trying to, let's say, have some kind of low disturbance or sinusoidal function that you're trying to get your system to behave like. But it leads to something called actuator windup, where if you look at our graph again, right? So if we have our desired step right here, and this is our system response, the entire area between the error is getting integrated, right? So you have this giant control effort going into here, right? And oftentimes what's going to happen is that you're going to saturate your motor. You're going to saturate your actuators. What that means is if you're starting to grow up like this, and your PID controller wants you to keep on going up like this, but at a certain point your motor's saturated. So you're only able to go up by that rate. And now you have this giant area that you're integrating, much longer than your integral control actually wants you to integrate it by. And that drives your system into an oscillation, right? So that can be quite bad for a system, so you have to deal with it through an anti-windup controller, right? Where either you'll eliminate the integral term as soon as you get to within a margin of your steady state response, or you either only enact your integral term within a margin of the steady state response. So a derivative term will also minimize a peak error, and it can react to changes before they actually occur, but it also increases your rise time. It also amplifies high frequency noise. Also, you need to low pass filter your derivatives, always. If you're using derivatives, you always want to low pass filter it, because if you have some kind of noise associated with it, you're taking derivative noise, you can get something that's pretty close to infinity, and all of a sudden you have a large input to your system, right? So if you use any kind of PID block in MATLAB, PID tool, it'll typically come with some kind of first order filter, or actually a 100th order filter, to take care of some of that noise. So this is our traditional PID control diagram. We see we have the proportional controller on the left, we have our plan on the right. We don't have any kind of sensor model in this case, and just using our general feedback closed loop system representation, we can dictate the system here. So what's interesting here, right? If we take a look, we can set this coefficient, we can set this coefficient, we can set this coefficient independently. So that's great for us, right? So if we know where our poles are going to be at, we can actually explicitly set these values to hit those poles. You'll see that in a second. So we decide those values given the performance requirements of our system, right? So the idea is to place the poles, the more negative, the faster the transient response is going to be, but also the greater overshoot. So I use something called ITAE design criteria to design some control gains for this. This is for the quote-unquote optimal gains. So as you can see, our rise time for the open loop system, which is in green, is about 8 seconds, whereas when you use the ITAE design criteria, you get that down to about 1.7 seconds, right? So it's a vast improvement over the open loop system. There is, however, a trade-off in that your percent overshoot is 30% versus 15% for the open loop system. So this is kind of an example I'm going to go through real quick. We've got 5 minutes. What if we have a really very strict design criteria, right? What if we need to make our closed loop system behave exactly like another second order system, right? We have some kind of actuator performance requirement that says that we got to have it within some kind of, can't escalate too much, it can't produce too much effort. So we're going to say that the performance requirements for our system are such that our closed loop zeta is going to be 0.7, and we're going to have a settling time of 4 seconds. And we also need there to be no steady state error. So in this case, we're going to say that TS must equal exactly 4 seconds. If you rise too fast, we might actually damage whatever the actuator is, or we might break the system. So we start off by examining the characteristic equation of the closed loop PID plant system. Right? So this is simply the denominator of this equation. That is our characteristic equation. So we have a third order system, but we want our system to behave like the second order system. Right? So if you look at the denominator, we have s squared for our desired system. In our actual closed loop system, we have an s cubed. So how do we make our third order system behave like a second order system? Do you guys have any ideas?
Linearization.
What is it?
Can you linearize that?
So it's already linear because we were able to do a Laplace transform. If our system was not linear, we would not be able to do a Laplace transform on it.
You have to get one of the roots to 0 in the S terms.
So there is one way to do this. So you can set one of your zeros to cancel out a pole. That's a completely plausible way to do it, right? But oftentimes that's not good, right? So what is it? I can't hear you.
Yeah, I think if you put a 0 in maximum gate.
Yep. Yep. So when you put in a 0, what you're doing, you still have that pole. You still have that state within your system. You just don't know what's happening to it. So also, let's say you have a pole on the right-hand side and you have an unstable system. You're trying to cancel that out with a 0. Any sort of modeling inaccuracy that you make is going to drive your system to instability. So if you're trying to cancel out a right-hand side pole with a 0, you better make damn sure that you know exactly the system you're doing, because any kind of error is going to drive your system to instability. So what we traditionally do to make our third order system behave more like a second order system is remember our poles and our transient responses. The closer they are to the imaginary axis and to the 0, the longer they're going to take. But the further they are away from it, the shorter they're going to take. So that means that by shifting a pole so it's significantly further away from the poles of our desired system, we can make our system behave like that second order system that we want it to behave like, even though it's a third order system. So if we can make that pole, so we would have 3 poles in this case, and we would have 2 poles in our desired system, we make the 2 poles that we want, bring that bad pole further to the left, we can make it behave such a way that it can approximately be a second order system. So we have this performance requirement for the settling time to be about 4 seconds. We go back all the way back to our second order system, and we look and we see that there's an empirical measurement that says, oh, okay, for our settling time, we can approximate it as this function of T of S is equal to 4 over zeta closed loop over omega closed loop. We solve that out, and that'll give us a desired closed loop frequency of 1.42 radians per second. So our desired characteristic equation then becomes this, right? So we know what our zeta closed loop is. We know what our omega closed loop is. So we can solve out that desired response times that pole, right? So for this case, we're going to say that the pole is equal to -3. I'm saying -3 because it doesn't actually need to be that far away from it for you to die off that response. So we set it up, and we then solve out each one of the coefficients for each one of the polynomial terms. Because these are just one unknown per equation, we're easily able to solve those out, right? So that gives us a Kp is equal to 7, a Ki is equal to 6, and a Kd is equal to 4. And that matches our closed loop system. It matches the poles of our closed loop system with the desired system, plus one pole that's going to have a quick transient decay associated with it. So let's take a look at the time response of the system. We have the open loop system in green, and we have our PID system in blue. So if you take a look, you can see that the rise time is still different, right? So we need our rise time to be exactly 4 seconds. The problem here is that our rise time is much less than 4 seconds, and part of our design criteria says that it needs to be 4 seconds or we break the machinery. So in this case, what do, right? The rise time is way too fast. We look at our desired system, we look at our closed loop system. Does anybody notice a difference between the two of them? So we know that our denominators are exactly the same. How about our numerators? We have 2 zeros in our actual system, whereas our desired system has zeros, no zeros. Right? So the zeros do affect the performance of your system. We set the denominators to be equal, but clearly the zeros must be affecting the performance of our system. And this is not a problem that we can fix by tweaking the gains, right? So theoretically, we could fix this by setting KD is equal to 0 and KP is equal to 0, but then that just completely craps on our design requirement for that we just made, right? So sometimes with really strict performance requirements, a single controller isn't enough to actually achieve those, right? So we got to add another controller to the loop. This is something called a pre-controller. So what we're doing is we're filtering our response by this pre-controller, or a desired response by this pre-controller. And we're also incorporating some kind of gain that we're multiplying our feedback by. Because essentially what we're doing with this pre-response controller is we're multiplying it times the gain. So that means that we have to multiply our system output times the gain as well to match that. So if we set our pre-controller to be P omega CL squared over omega n squared over 1 plus KPS plus KI plus KDS squared, if we look back and we multiply each of s times that value, you'll see that the numerator and the denominator will cancel out. We also need to find this K term that will match that frequency, right? So we have our pre-controller that'll make our system behave like the second order system, but now we actually have to find that K term. Are you guys familiar with final volume theorem? So the limit as t goes to infinity of any function y of t is equal to the limit of s goes to 0 of the transfer function of that function times s. So for a non-pre-filtered PID controller, we have y of s is equal to over r of s is equal to omega n squared times the transfer function. We say that a step input r of s is equal to 1 over s. We take a look here and we see that this s cancels out with this s. We drive all of our s's to 0, so this goes to 0, this goes to 0, this goes to 0, this goes to 0, and this goes to 0. All we're left with is omega n squared times ki over omega n squared times ki, which is equal to 1, which is exactly the response that we want from our system. So for the non-pre-filtered PID, we're okay with that, right? We know in our system we're not okay because we're still getting 1, but we're not getting 1 at the rate that we want to get 1 at. So let's take a look at the pre-filtered system, right? So we use final value theorem again. We see that we have the numerator canceled out now, and we just have that straight gain. We set up the final value theorem of limit of y of s, so it'll be s. Again, we have a step input here, 1 over s. S cancels out with s. This cancels out, this cancels out, this cancels out. So we have P omega CL squared over omega n squared K times Ki. So now we're trying to solve out for K. This, we want that to be equal to our reference, which is 1. So we set that equal to our reference, which is 1. We solve out for K, which gives us this value here. We check the time response of our system. Open loop is in green. Or actually, the desired response is in green. The PID is in blue. The pre-filtered PID is in red. We now match our desired response much more closely, simply by adding a filter to what our desired response, to our desired value. So I'm going to conclude now. Only 5 minutes over. It's not too bad. So general control rules of thumb. There's always a trade-off between robustness and performance. So you can't have a great, well-behaved system with very quick settling time, with little overshoot. That can also reject heavy disturbances. You got to make a compromise to get both. Controllers do not take into account actuator properties, right? So this goes back to that interval wind-up that I was talking about. Your linear controller has no knowledge of your actuators whatsoever. In fact, most actuators are on nonlinear because you can saturate them out. And that's nonlinearity, because you're going from, right? So you have some kind of piecewise continuous function, which is inherently nonlinear. So linear controllers have no way of dealing with actuator saturation, so you have to add in a heuristic to deal with that later. The accuracy of your best controller is roughly only 10 times that of your navigation system, right? So pick out good sensors, right? Because the best you could ever do is 10 times whatever your sensors are. When placing poles, the more negative you shift the pole, the more control effort will be. So that goes back into your controllers having no actuator knowledge, right? So if you try making that pole, like instead of going from -3 to -100, you're going to have a lot more strain on your actuators, and your actuators might not be able to accomplish that. So these are a bunch of courses that we offer at FAU that are great controls courses. Marine vehicles is offered once every 4 years. Underwater vehicle navigation is great when it comes to sensor design and Kalman filtering and all that fun stuff. Intelligent underwater vehicle autonomy is kind of like a tour through all the control systems. So you'll actually go through and dynamically model an AUV and then design a controller for it. Linear controller, sliding mode controller, adaptive controller. You get a tour of all the different control domains. Dynamic systems with Dr. Ahn. Sounds like some of you guys have already taken that. Mechanical controls with Dr. Maestri. That is a great course, by the way. That is probably the most useful course I've ever taken in my life. This is something that I do constantly. Mechanical controls with Dr. Maestri. Modern control systems with Dr. Wang and EE, that's good too. Biosystems modeling and control with Dr. Ra. That was actually a really great course on nonlinear systems. Controls 2 with Dr. Ra is also good, although I have not taken it. And digital signal processing with Dr. Bojan, which is an incredibly useful course. And I got a couple texts. This is the best controls introductory textbook there is. So that is Dorff, Modern Control Systems. This is the easiest to understand nonlinear control text that there are. And this is actually a pretty good one, an introductory text as well. It's actually really, really dense, so there's a lot of information in there. And nonlinear systems with Khalil is pretty much the defining nonlinear controls text. Right? So I've talked for 2 hours straight. Do you guys have any questions?
Thanks.
Yeah.
I dumped a whole lot of knowledge with you guys. I really don't expect all of you to learn everything immediately.
So for those who came in, this is what you are able to.
Yeah. Are you okay with providing lecture notes?
I am okay with providing whatever you guys would like.
That would be awesome. Yeah. Like so much to Google, it's crazy.
So then I'll put the video up on the YouTube page.
You got it.
I'll link to the PowerPoint slide in the